So we've said that one of the big problems that we're going to end up working in the introductory level physics class is going to be vector addition problems. And so we need to be very, very comfortable working them. And so hopefully at this point we're good breaking vectors up into components, and we're going to take advantage of that to work vector addition. So for starters, what does it mean to add vectors? Well, basically, here's our vector equation, and it looks pretty familiar, right? It's just an addition equation, but it says that we're going to create a new vector r, the resultant, by adding together, in this case, three vectors, vector A, vector B, and vector C. So in terms of the picture that goes with this, basically what this says is, well, if you walk along vector A, so start by walking along vector A, then turn and walk along vector B, then turn again and walk along vector C, that this A plus B plus C is going to give you the resultant. So effectively, vector addition is just another way of saying that you're just lining the vectors up so that they come one right after another, and then you're going to connect from, so this process is known as tail to tip. So I'm lining up the tail of one vector with the tip of another. It's just another way of saying I'm drawing them consecutively. And then my resultant goes from the point where I started, the first tail, to the point where I finished up the last tip. So this is graphically what we mean. And so one of the things you'll notice is there are actually two very useful vector diagrams here. One is the vector diagram where I draw all the vectors from the same origin. This one is really useful to break vectors up into components. The other is when I go ahead and draw out the vector addition process. So I draw all my vectors tail to tip, tail to tip. This one is useful to see that resultant r, and denoting what the angle r makes in terms of trying to figure out its direction. That's often really useful looking at this diagram where I've drawn out the vector addition. So the other thing to emphasize is that the order doesn't matter. We still would have gotten the same vector r had we drawn C first, and then A, and then B, right? It would have ended up being exactly the same. So the order doesn't matter in our vector addition problem. All right, so let's take our example here, and again, we're just going to have three vectors. We'll keep this as general as possible, so we'll just call these magnitudes A, B, and C. We've got our three angles, theta A, theta B, theta C. And so what we've said is we're going to redraw this as a vector addition. So here's all three vectors from the same origin. Here's the vector addition problem, and again, I can see my resultant. And so what I can do now is I can break each vector up into its components. So vector A breaks up into A cosine theta A, A sine theta A, given my choice of coordinate system, x component positive, y component positive. Vector B, it's going to have a positive x component but now negative y component. And so again, here's my B cosine theta B minus B sine theta B. And then vector C, well, this is going to be negative x, negative y, because it points back to the left and down. So negative C cosine theta C, negative C sine theta C. And so basically our vector addition problem, again, we had it as written as a vector equation. And all that means is that we get to do one addition problem per dimension. So we'll have a Rx is equal to Ax plus Bx plus Cx, right? The x component of the resultant is the sum of the x components of your three vectors. And then the y component of the resultant is the sum of the y components of your three vectors. So again, we get to do, when we look at that initial vector equation, where we said r equals a plus b plus c, but that all those were written as vectors, that's really hiding one equation per dimension. And since we have two-dimensional vectors here, we really need two equations. The other thing to notice is we don't want to mix these things. So this is all x components in this equation. This is all y components in this one. If we think about what's going on in our picture here, and you can see the x component for the resultant, the y component for the resultant. And if you think about sort of where that's coming from, well, in terms of just x components, so just horizontally what went on, we walked this distance to the right along vector A, a further short distance to the right along vector B, then walked back this distance to the left along vector C. And so from where we started to where we finished up tells us horizontally what's that x component of our resultant. So you can see that basically the x equation is just keeping track of the horizontal pieces of the vectors. And that's all we're doing here in setting up this equation. Similarly with y, same idea, right? Along vector A, we went up some short distance, then we came back down a larger distance along B, then down even further along C, and so I end up with a component of the resultant, a y component of the resultant that happens to be negative, and is basically equal to just add up those three components of my individual vectors. So pictorially, all we're doing in a vector addition equation, or when we work vector addition problems, is just keeping track of what goes on horizontally and what goes on vertically, if that's our choice of coordinate system. So our process then, well, we're going to start by drawing vector diagram. And again, remember, there's really two that are useful. We can draw all the vectors from the same origin because that's useful in terms of breaking vectors up into their components. Or we can draw the vector addition problem because that's useful in terms of seeing the resultant. We're going to need to pick a coordinate system. Sometimes this will be given, oftentimes this will be left to us. And it doesn't matter what coordinate system choice we make as long as we sort of label what that is and are consistent with our choice. Then we need to break each of our vectors up into their components. So if we look at, say, vector A, let's say it has a magnitude of 12 meters and points in the positive x direction. So I know that it's going to have an x component of plus 12 meters and a y component of 0. Vector B, let's say it's got a magnitude of 15 meters and points in the negative y direction. So again, I'm going to have a x component of 0 now, since it lies along the y-axis, and a y component of negative 15 meters. Vector C has a magnitude of 15 meters, but points in this direction 36.9 degrees above the negative x-axis. So it has two non-zero components, and so I need to use my trig functions to break vector C up into components. So I need a negative x, positive y, the magnitude of vector C is 15, and then since I've defined this angle relative to the x-axis, the x component is going to get the cosine of 36.9 degrees. And when I work that out, I get that the x component for vector C is negative 12, the y component for vector C is positive 9. So when I break those vectors up into components, and again, the way that I'll probably do it most often in class as we're getting comfortable with this process is to do it in a table. Then here are the components of our individual vectors, and that set us up to go ahead and set up our two equations. So the next step is we're going to add the x components of the vectors together to get the x component of the resultant. So literally it is this plus this equals that. So x component of A plus x component of B plus x component of C equals the x component of the resultant. Here you notice what that gives us is 12 plus 0 minus 12, which equals 0, which is why our resultant lies along the y-axis. It has a 0 component for x. Then I need to do the same thing in y, right? I have two-dimensional vectors, so I have two equations that I'm really setting up with my vector equation problem. So y component of A plus y component of B plus y component of C equals y component of the resultant. So this is 0 minus 15 plus 9, and that tells me the resultant has a y component of negative 6. So again, it points down with a magnitude of 6 meters. So this is how we get the magnitude, or how we get the components of the resultant vector. And then again, once we've got the components of our resultant, then we can figure out magnitude and direction by Pythagorizing and using our inverse tangent function.